You're watching a Channel 98 NBISD TV production.
Hey, welcome to Deja Vu. It's Algebra 2. I'm your host, Kevin Corpy, just doing a little doodling back here on the board. Thanks for tuning in today. We got a great show, as always, for you today. Today we're going to be looking at polynomials once again. But today we're going to be looking at how to factor polynomials, and we're going to be looking at a special form of division that's less filling and lasts longer called synthetic division. So, if that intrigues you, download the worksheets from the DISC website and stay around for about 30 minutes or so, and you'll hopefully have a lot of fun and learn a lot. Lesson 15, polynomials, factoring and synthetic division, the one you've been waiting for. Okay, there's a lot of theorems on today's episodes, and theorems that you have to actually know the implications of. The name's really not so much important, but the implication of the theorem is very important. So in class or on the show, you've got to memorize them. And I'm going to show you how these theorems come into play into factoring and synthetic division. Okay, so here we go. The first theorem of the day is called the remainder theorem. Now, anytime a theorem has its own special name, rather than just like theorem 5.7, then that means it's a very important theorem. Now, a theorem has two parts. It has a hypothesis, which is the if part, and then it has the conclusion, which is the consequence, the then part. So if the if part is true, then the then part, is automatically true. So here's the if then. It says if we have a polynomial, call it p of x, is divided by this linear factor x minus a, then we know that the remainder of that division is r, and it's actually p of a, which means in function notation that is the polynomial evaluated at a, which is the root, incidentally, of this linear factor. It's the value that we get when we plug it in for x gives us a 0. Okay? So dividing by x minus a, the remainder is going to be the function evaluated at a. Got it? Let's see how that comes into play here. We want to take this fourth degree polynomial p of x, x to the fourth minus 2x cubed plus 3x plus 1. It's written in descending order. And we want to divide it by this little linear factor x minus 3. Well, what we want to know is, what is the remainder? Well, there's a couple of ways we can do this. Let's kind of look at the actual operation. How would we find the remainder if we didn't know what the remainder theorem was? Well, we could do long division. Let's do a quick version of long division. If you're going to do long division, what you want to do is take your dividend, x to the fourth minus 2x cubed. There's no x squared term, so I'm going to put plus 0x squared plus 3x plus 1. And then we're dividing it by x minus 3, which is our divisor. Okay, now this is long division of polynomials. You look at the first term in your divisor and the first term in the dividend, and you say x goes into x to the fourth, x cubed times. And that's going to become your quotient. So we write it up there. Now we'll distribute from on high, and we get x to the fourth minus 3x cubed. And then the all-important step is to subtract. So we have to change both signs. Now if you did it correctly, you should get a 0 here. X to the fourth minus x to the fourth is 0. But over here we have 3x cubed minus 2x cubed. That gives us a 1x cubed. And just like in division of numbers, we bring down the other terms. Okay, so we get that. Now we do it again. X goes into x cubed, positive x squared times. So we put plus x squared up there. And then we distribute from up top. X squared times x is x cubed. Those should be the same number at this point. X squared times negative 3 is negative 3x squared. And we have to change both signs. Okay, we get a 0 again. And now I get 3x squared plus 3x plus 1. Now we continue on. X into 3x squared, we need a 3x. So that when we multiply 3x times x, we get the 3x squared. But we have to distribute to all of them. So 3x times negative 3 is negative 9x. And we change both signs. And I get 9 plus 3 is 12x. Bring down the 1. And we're almost done. X into 12x, well, that goes plus 12 times. 12 times x is 12x. 12 times negative 3 is negative 36. And then we have to change both signs. And look what we get. 36 plus 1 is 37. Now x, a linear or degree 1 term does not go into a constant degree 0 term. So this right here is in fact our remainder. Okay? So is there a better way to find it? Well, today we're going to be looking at synthetic division as well. This is long division. Synthetic division is really the same operation. You get the same result, but it doesn't have all the x's carried along with it. So here's synthetic division. You've probably done it in class. You're just going to write down the coefficients of your divisor in descending order. So I have a 1x to the fourth, a negative 2x cubed, a 0x squared. You need a placeholder if there's no x term there, a 3x, and a positive 1. Now here's how synthetic division is different. Instead of dividing by the factor x minus 3, we're going to divide by its root. That is the value that makes it 0. So that is going to be 3, because when I plug in a 3 for x, I get 3 minus 3, which is 0. So I'm going to put a 3 down here in this little box. Now here's the operation. We always bring down the first number, which is a 1, and then I multiply on the bottom row. So 3 times 1 is 3. I place that number up here, and now I have a column. I will add, ooh, that's not a 21, stray mark. I add vertically. 3 minus 2 is 1, and I multiply again. 3 times 1 is 3, plus 0 is 3, times 3 is 9, plus 3 is 12, times 3 is 36, and then I add vertically and I get 37. Whoa, I'm going to put a little back angle on this. That last box is your remainder box. Cool. That's the same thing we got over here, 37, but it's much more efficient. Now notice what else synthetic division allows us to do. You remember our quotient up here, 1x cubed plus 1x squared plus 3x plus 12? Well, look down here. These numbers right here are the coefficients of the quotient of the depressed polynomial, meaning it's 1 degree smaller. If we started with an x to a fourth, this is going to be 1x cubed, 1 degree smaller, plus 1x squared plus 3x plus 12. So synthetic division is a really nice way to divide by a linear factor. Now we got a remainder of 37. So what do you know about division with numbers? If you get a remainder that's not 0, then we really say that that number is not a factor, but we can still do the division. Now let's go back to the remainder theorem. The remainder theorem says that if we divide by x minus a, it's just the polynomial evaluated at the root, in this case at a, or in this specific case at 3. So we could have found the remainder without actually doing the division by using the remainder theorem. So what is p of 3? Well, if you look up here, it's going to be 3 to the fourth minus 2 times 3 cubed plus 3 times 3 plus 1. And all we have to do is evaluate that. Well, 3 to the fourth is going to be 9 squared, which is 81. I get 3 cubed, which is 27 times 2, which is negative 54, plus 9 plus 1. So that's going to be an 81 minus 44, which guess what is 37. Whoa. So here's what's nice about the remainder theorem. It basically allows you to find the remainder. But notice that the remainder itself, when I plug it into the function, is the y value of the actual graph of the polynomial. In other words, we have a coordinate called 337 that this polynomial's graph has to pass through. Remarkable. You can already kind of see the theoretical implications kind of weaving together. So now we're going to look at a version of the polynomial that's not the standard form. We're going to call it the nested form, tweet. Okay, so here's a nice little nest. Why is it called nested form? Well, let me show you. This is kind of going to give us an idea of where the synthetic division comes from. I mean, who thought up that process? Well, it comes from the nested form. Nested form is basically grouping together all of your terms that have an x in them. Now I'm going to rewrite it, and I'm going to put a placeholder for my missing x squared term. So that'll be plus 0x squared plus 3x plus 1. Okay? Now here's what we do. We're going to group together all the terms that have an x in it, which is all but the constant at the end. And we are going to factor out an x, and we're going to factor it out on the right. So that's going to leave me an x cubed minus a 2x squared plus a 0x plus a 3 all times that x that I factored out plus 1. And now I'll repeat the process. So now I group those terms together, and they all three have an x, and I'll factor out another x on the right. So that's x squared minus 2x plus 0 times the x. Okay, so there it is. And then everything else still stays the same. I still have plus 3 plus 1. And I'm going to keep that process going. Now I have to group these two together, and I'm going to factor out an x. So I have open, 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 x minus 2, and then I have the x that I factored out, and then everything else, the plus 0 times x plus 3 times x plus 1. This is called nested form. Now nested form kind of has implications for programming, because your calculator can actually handle, or any program can handle, evaluating a function like this, just direct substitution. But raising something to the fourth power, especially for values of x that are larger than 3, those can get very large very quickly. The nested form is an equivalent version of the polynomial. So look what happens now if I try to evaluate p of 3. The order of operations say to do parentheses first. Okay, so this is my innermost set of parentheses. So look what's going to happen. I plug in a 3 minus 2. That's a 1. That's the small number. Times x, which is 3. So that's going to give me a 3. Plus 0 is 3. That's easy. Times another 3 is 9. Plus 3, that's 12. That's easy. Times 3, that's 36. Plus 1, ooh, that's 37. I never had very large values at all. So this accomplishes the same thing. And in general, a computer program that can do the same thing multiple ways, the way that's going to keep it running faster is when the numbers are smaller. So this is a faster way to program something to evaluate a function. But notice that what we did right here when we did our synthetic division was really the same thing. We brought down the 1 and we went 3 times 1. And then we put it up here and we did 3 minus 2. That's the same thing we did right here, 3 minus 2. We brought it down, then we multiplied by the 3. That's what we did there. And then we added it to 0. That's what we did there. And then we multiplied it by 3 again. That's what we did here. We brought it up and added it to the 3, like right there, to get a 12. And then we multiplied by 3 again and added 1. So the nested form, or the sequence in nested form, is exactly where the synthetic division algorithm or process comes from. It wasn't just pulled out of the sky. Okay? So there is an important result now, though, that comes from synthetic division. And here it is. Synthetically dividing a polynomial by x minus a is equivalent to synthetically substituting x equals a by the remainder theorem. Okay? We just have to remember to write our coefficients in descending order and put a placeholder for any missing x. Okay? Very important consequence. So you're probably wondering at home, okay, great, so I get a remainder of 37. What if the remainder is 0? Okay, that's what we're hoping for, really, if we're trying to factor, right? We want it to go in evenly. We want a remainder of 0. Well, that leads us to another important theorem. Now, this one I just entitled theorem. I don't know if it has a special name. Give it your own name. It is important, though. Here's what it says. It says, if a polynomial p of x, again, is divided by x minus a, and the remainder happens to be 0, then x minus a is, in fact, a factor of the polynomial. Just like 36 divided by 4 is 9, remainder 0. That means 4 is, in fact, a factor. And so is 9, by the way. The quotient would also be a factor. So that's what our goal is. Okay? Now, by the remainder theorem, why does that work? That means plugging in our a gives us the remainder, which in this case is 0. But remember, this is an ordered pair. That means that x is a and y is 0. And on the graph of our polynomial, anything with a y-coordinate of 0 will actually reside on the x-axis. So we call that an x-intercept, or we call it a root. Ooh. Now the consequence of that leads us to a very important theorem. And we call it the factor theorem. And this one's hugely important. It's actually an if and only if. Here's what it says. A polynomial p of x has linear factors, or a linear factor of x minus a, if and only if x equals a is a root of the polynomial, or is a 0 of the polynomial, or it's an x-intercept of the graph. So it's an if and only if, which means we can go in reverse. If x equals a is a root, then we know x minus a is a factor. So that ties them closely together. If we know a root, we know a factor. Or if we know a factor, a linear factor, we know a root. Very important. And why are roots so important? Well, they keep the trees anchored, right? But in mathematics, the roots of a polynomial equation, especially if that equation models real-life behavior, are going to be the answers that we're seeking out. They're going to answer our questions, and that's why roots are important. Okay? So basically, that's why factoring a polynomial is so important, because if you're staring at your factors, you're really kind of implicitly staring at your roots. All right, let's take a quick break. We'll watch some valuable public service announcements, and we'll be right back, so don't go anywhere. While you're gone, think about this. Where did the lonely mathematician eat his lunch? The answer when you get back.
When you give up the ability to decide for yourself, you give up what makes you, you.
Twinkle, twinkle, little star, how I wanna know what you are. Up above the world so high, like a diamond in the sky. Twinkle, twinkle.
The odds of a child making it to Broadway, 1 in 11,000.
You.
The odds of a child being diagnosed with autism, 1 in 150. You know the odds of autism. Now learn the signs. Go to autismspeaks.org.
Welcome back to Deja Vu. It's Algebra 2. I'm your host, Kevin Corpy, talking to you today about polynomials and synthetic division and factoring. Okay, so where did the lonely mathematician eat his lunch? He ate it at the multiplication table. Oh, yeah. All right, back to the math. Okay, so let's go ahead and verify now that given the root x equals -3 for this polynomial, we want to verify that x equals -3 is a root, which if it is, x minus -3 or x plus 3 would be a factor. Now we're going to do that using synthetic division. And rather than just plugging in a -3 and raising it to the 5th power, those numbers are going to get very big very quickly. Synthetic substitution is kind of like the nested form. So we write out the coefficients, 3x to the 5th, 18x to the 4th, 27x cubed, 0x squared, 0x, and 0 for the constant. So we need trailing zeros here. So let's go ahead and do the operation here. We always synthetically divide with the root, not the factor. So that's -3. So here we go. Bring down the 3, and then we multiply. That's a -9, and then we add. 18 minus 9 is 9, times -3 is -27. We get a 0 here already, but we're not quite done. 3 times 0 is 0. We add, we get a 0. Times -3 is 0. Add, get a 0. 0 times -3 is 0. Add, and you get a 0. So there's a bunch of zeros there at the end. But we had to go through that operation. This 0 now is the remainder. So if we get a remainder of 0, that means that this is a root, which means that x minus -3, like I said, which simplifies to x plus 3, is a factor. So once we know a factor, we can now write p of x as x plus 3 times another factor. Well, remember what I told you before? These numbers down here give you the coefficients of the quotient. Okay, and it's 1 degree smaller, so it's the depressed polynomial. Not depressed because it's in a math class, but depressed because it's 1 degree smaller. So if we started with a 5th degree polynomial, now we're 4th. So this would be 3x to the 4th plus 9x cubed plus zeros the rest of the way. So there's another factor. So synthetic division, knowing a root but not knowing how to factor, is a nice aid to factoring. Okay? So basically, again, staring at this linear root, x plus 3, or factor, sorry, we're staring at the root. It's the value that makes that 0, in this case -3. And the master of all stares, at least if you're a batter in the baseball, National or American League, is Roger Clemens. He's staring down the roots, much like you can if you have it factored. Okay? Let's look at this other example down here. We got x to the 5th plus 18x to the 4th plus 27x cubed equals 0. It's actually the same one. What do we want to do with this? Well, we want to try factoring it a little bit differently. There's another way to factor. What if you don't know any of the roots? Well, you can factor by looking for common factors first. So notice in these three terms I have a 3. That's a number that's a common factor. And I also have an x cubed. So I can actually factor those out of each of the three terms. So I'll get 3x cubed times, and I'm just left with x squared plus 6x plus 9. Okay, so this is partially factored. I'm still going to equal to 0. Well, now I can focus in on trying to factor that some more. And factoring quadratics is something that hopefully you're comfortable with. Factors of 9 that add to 3. Well, that's going to be x plus 3 times x plus 3, or x plus 3 quantity squared. And it's still equal to 0. So notice what we can do here. We can actually write this in x minus a format. And we can basically expand it out. We get 3 times x minus 0 times x minus 0 times x minus 0. That's the same thing as x times x times x, or x cubed. This one I already have expanded, x plus 3 or x plus 3. So here's where the factor theorem is handy. I can set each of these equal to 0, but basically, remember, if I'm staring at the factors, I'm staring at the roots. So here's the roots. So the values that make each of these factors 0. So it's going to be x equals 0, or x equals 0, or x equals 0, but I repeat myself, or x equals -3, and x equals negative 3. Well, that's only two distinct numbers. But notice that they occur 3 times for the 0 and twice for the negative 3. Now that has very special meaning because we call 0 in this case a triple root. Okay? A triple root because it occurs 3 times. Or we say that it has multiplicity of 3. I abbreviate multiplicity M3. X equals negative 3 because there was 2 factors occurring. There's 2 roots of occurring. We call it a double root. Okay? Or we say it has multiplicity of 2. Now incidentally, here's the graph of that function. And you can clearly see that the x-intercepts are negative 1, negative 2, negative 3, and 0 right there. But notice how the multiplicities affect the way it crosses or touches the x-axis. This one right here is a multiplicity of 2. And it appears to be coming up to the x-axis and boing, bouncing right off of it. Okay? This one down here is more than just crossing it. It's actually coming up and kind of wiggling a little bit. It's acting as if it's going to turn around, but then it's like, psych, and it goes back up. So this one right here, it kind of wiggles a little bit as it's crossing the x-axis. So we have a bounce, essentially, and a wiggle, which we actually call an inflection value. So that right there, the way it touches, is related to the multiplicities. And notice that the multiplicities are nothing more than the exponents on the factors. Okay, let's summarize that. Okay, so let's summarize here. We know now that the factors in the equations give us the x-intercepts, or the roots. But by that last example, we also know that the exponents on those factors, or the number of times that they occur, affect how the x-intercepts look. Okay? And there's 3 distinct ones that you at home are responsible for knowing strictly from the equation how they look on the graph. 3 distinct types. We have the ones that just appear to come down and cross. I mean, there's nothing funny going on. This guy is crossing the x-axis. Okay, that's like a railroad crossing. I'm going to call that a multiplicity 1. Nothing funny going on. It's a single root, M1, multiplicity 1. But then we have these types here that come around and they seem to bounce off the x-axis. Okay, like a bouncing unicorn leopard. So that would be an M2 or a multiplicity 2 or a double root. Okay. Then we have these over here that seem to wiggle as they cross the x-axis, and we call that an inflection point. Okay? It inflects across the x-axis much like this wiggly worm, and that is an M3 or a triple root. So we have an M1 crossing, an M2 bounce, or an M3 inflection or wiggle. Okay? And these are in fact the exponents. Now, let's look to see what this equation actually is. It's this polynomial right here. It's a 6-degree polynomial. Here's where the factor theorem comes in handy. We actually know what the roots are, and we know their multiplicities. So right here, I know that that's a cross at negative 1, negative 2. So x equals negative 2 is a root, and it's a multiplicity 1. This right here is x equals 0, and it's a multiplicity 2. And this over here is 1, 2, 3. That's x equals 3 with a multiplicity of 3. So what does the factor theorem tell us about this, which is not factored? We can factor it. Watch this. We're going to call it p of x. Now, I'm going to leave a little space here in the front. I'm going to use the factor theorem. If negative 2 is a root, then x minus negative 2 or x plus 2 is a factor. The multiplicity it's across is 1, so that's its exponent. If 0 is a root, then x minus 0 is a factor. If it's a double root, it's a bounce. Multiplicity 2. If 3 is a root, then the factor theorem says x minus 3 is a factor. Since it's a wiggle or an inflection, we know it's multiplicity 3, so the exponent is 3. Now what we need to do is make an allowance for some type of vertical stretch. Remember we talked about vertical dilations on a previous show. In the front, call it a. And so long as a is not equal to 0, this gives us all the different varieties of this equation. Okay? If you knew a point on the graph itself, you could actually plug it in for x, and you could solve for a to figure out what it is. All right, so there you go. The multiplicities are the exponents, and if you know the roots, x minus those roots are the factors. It's an aid to factoring. Now it's time for
Deja Review.
Okay, that's cool. I love that. We are going to now take the same equation, and we're going to synthetically divide. In this case, we know what all the roots are, but I'm going to show you that it should work. So this will be a good review of synthetic division as well. We're going to write out all the coefficients. So I have 1x to the 6, negative 7, and then I get a 9, a 27, a negative 54x squared, and then I have 0x and 0 from my constant. Now, remember what my roots were. I'm going to actually use my roots, and I'm going to do them kind of in the order from left to right. So let's do negative 2 first. It's a single root. So I should be able to synthetically divide with the negative 2. Here we go. It's going to be long, but the process is the same. We bring down the 1, and we multiply. Negative 2, add negative 9. Get positive 18. Plus 9 is 27. Multiply negative 54. If you add, you get negative 27. And now if you multiply, you get positive 54, which gives you 0. You multiply, you get 0. Add, you get 0. Multiply, you get 0. Add, you get 0. Now box off that last one. We got a 0. So that means that negative 2 is in fact a root, and x plus 2 is a factor. We already knew that, so we're confirming it. But now what we can do is we can keep going on this quotient, on this depressed polynomials, with the other roots, because we haven't factored them out yet. They're still a factor of this remaining polynomial. So what was the next one? The next one was a 0, and it was a double root. So watch this. I'll go ahead and do a 0 now on what's left. So this is repetitive synthetic division. You bring down the 1 and multiply, and you get 0. Add, you get negative 9. Multiply, you get 0. That's 27. Multiply, you get 0. Add, you get negative 27. Multiply, and you get 0, 0, 0, 0. Hey, it worked. Now, because 0 is a double root, it actually works again. Watch this. We're going to keep going on our depressed polynomial. We started with degree 6, so this down here was degree 5. We're already down to a degree 4. These are the coefficients of a degree 4. Let's do a 0, and that should take us down to a degree 3. Bring down the 1 and multiply. That's a 0. Negative 9 times 0 is 0. Add to get 27. Times 0 is 0. Negative 27 times 0 is 0. Add, and we get another 0. A lot of zeros going on here, but that's okay. The zeros are at the end are the ones we want. So I've used up my 0. This is now a degree 3. Well, look at this. X equals 3, remember, was a triple root, so it'll work 3 times. Let's try it. I'm going to use a 3 here. And now I'll bring down the 1. I'll multiply, and I get a 3. Add and get a negative 6. That's a negative 18, which gives me a 9 times 3 is 27. And looky there, I get a 0. Well, it's a triple root, so it should work 2 more times. This is now a quadratic down here. I'm going to keep going with my 3. Bring down the 1, 3, negative 9, 0. Boom! This is linear, degree 1. One more time, we know one root. It's a 3 again. It's a triple root, multiplicity 3. Bring down the 1, multiply, you get a 3, and you get a 0. Ooh, and we get a 1. This down here is your last remaining factor. That's your constant factor. It's degree 0. And so what that essentially is the prime factorization, essentially. We know that one of the factors is x plus 2, x minus 0, or just x, times x minus 3, times x minus 3, times x minus 3, times 1. So essentially, if you do it this way, you really know now what that value of a was in this problem. It was a 1. If this number here would have been a 5 or something, it would have been a 5. Okay? So it takes a little bit of practice, and you've got to understand the theorems to be able to figure out how they all weave and blend together. But a lot of practice, and I think you'll have it. It's a lot of fun, actually. All right, great show today. Unfortunately, all good things must come to the end, and we are at the end of the show because we're out of time. So I hope you tune in next week for another valuable episode of Deja Vu, it's Algebra 2. Until then, I'm your host, Kevin Corpy, reminding you to do your homework.